Welcome back to 5-Minute Chemistry. Today we are going to introduce the concept of electronegativity and we will talk about bond polarity. So, why do we need this electronegativity concept? Well, if we are talking about covalent bonds, in covalent bonds, two atoms share 2, 4 or 6 electrons between each other to fill up their valence shells to the octet structure, which is the stable configuration for them. And if the covalent bond is between two atoms of different elements, there might be a difference in terms of how strong the nuclei of these atoms will try to attract the electrons towards itself. If we have the atoms of the same elements, of course, then this strength will be the same. So the electrons will spend the same time around both of the atoms that are bound together in this covalent bond. But if this covalent bond is between two atoms that are of different elements, this strength might be different, which means that the electrons will spend more time around the atom, which binds them more strongly. So electronegativity is a concept that was introduced to be able to have a relative scale of how much each element is attracting the electrons in a bond. So electronegativity was originally introduced so that the element which has the strongest atoms in terms of grabbing electrons, which is fluorine, to have the number 4 for its electronegativity, and the weakest one is a francium. You can find it in the bottom left corner of the periodic table. So that atom is binding the electrons in a bond the weakest, and that became 0.7. And electronegativity is not something that you can just measure. It was originally made up by comparing the different compounds and trying to have like a relative scale for the strength of the atoms grabbing on the electrons. But there are also methods in which you can calculate the electronegativity from actual physical parameters, or actual parameters that can be measured. And so this is why in this specific instance, fluorine is not exactly 4.0, but 3.98. This is a calculated value for its electronegativity. While it would make no sense trying to memorize all the electronegativities for all the elements, there are a few important things here that is good to remember, and that is when we are going in the periodic table from left to right, the electronegativity rises. If we're going in the periodic table from top to bottom, then the electronegativity is going down. And this is why all the highest electronegativity elements are in the top right corner. Of course, you have to exclude the noble gases that don't form any compounds. And there are, of course, a few elements which we just don't have any information on their electronegativities yet. Besides this, I think it is a good idea to memorize the 4 elements with the highest electronegativities. So fluorine is the highest one, and then the second one is oxygen, which is followed by chlorine, and the fourth one is nitrogen. In some of the textbooks, you might find nitrogen and chlorine to have the same value. It's based on what kind of model was used to calculate the electronegativities. Okay, so from electronegativity, we can move on to the concept of polar bonds. So generally, if you just have a bond between the atoms of the same elements, like an oxygen double bond here, that will be nonpolar because here we bond together two neutral atoms and the electrons are shared equally, so there should be no charge on either of the oxygen atoms. The charges of the electrons are cancelling out the charges of the protons in the nuclei of these two atoms. If we have two atoms that are different elements, so like carbon and hydrogen, but the electronegativity difference is not large, then there will be some difference on how much time the electron spends on one atom versus the other one, while this bond is binding together two neutral atoms. Because the electrons spend a little more time on one side than the other, you can find that the electron density will not be exactly equal, but this difference might be so small that, for example, for carbon and hydrogen, the organic chemists who work a lot with carbon and hydrogen bonds will consider this a nonpolar bond. If the electronegativity difference is much bigger, like in the case of hydrogen and chlorine, then the time the electrons spend around one of the atoms, so in this case chlorine, will be much higher than how much time they spend around the other atom, which is hydrogen in this case. And so we can see that there will be a much bigger difference between the electron density. So here the purple shows that the electrons spend much more time on that right hand side, and the yellow shows kind of the electron deficient state because the electrons don't spend that much time around the hydrogen. And this means that because the electrons spend less time around the hydrogen, the positive charge of the protons on that side will not be balanced out totally, so there will be some positive charge over there, and over the chlorine side, because the electrons spend too much time there, that will be somewhat negatively charged. So these delta plus and delta minus symbols are used to show that these atoms carry some charge which is much smaller than the actual electron charge which we would have in ions. But because there is this positive pole and the negative pole in this bond, this is called a polar bond, and these small positive and small negative charges, because of the electrostatic force, this will have some impact on how the molecule that contains this polar bond interacts with other molecules. And in the most extreme case, so for example sodium chloride, where we have an ionic compound, usually in this case the electronegativity difference is very big, but it doesn't really matter because we are not talking about a covalent bond anymore, we are talking about ions bound together by ionic bonds. So in this case the electron is not shared, so we just have a positively charged cation and a negatively charged anion. Of course, life is not always this simple, and there will be some compounds which will have mixed covalent and ionic characteristics, but today we don't have to go into that. So, this is it for today, and I will see you tomorrow.